Okay, so here's what I want you to do. So here we have the example of a thick wire. We looked at this current distribution last week. So what we have is a thick wire with a current K times S. So K is a constant, so that means that the current is 0 at the very center of the wire, and then it increases and is the largest on the surface of the wire. The current's in the z-hat direction, so the way I define the coordinate system, the current's coming out of the page again, and the radius of the wire is r. So basically, I want you to go through all the steps you need to find the magnetic field both inside and outside of this wire. And again, I'm drawing cross sections. They're what make the most sense for solving these problems. So the first thing you need to do is sketch the direction of the magnetic field. Then you need to define the Amperian loop, including the path direction. Now you can define that path direction clockwise or counterclockwise. It's up to you, but just make sure you're consistent so the path direction matches up with your dA direction. Okay, then you need to find what the path integral is. You'll need to define dA. Again, make sure you're defining that consistent with your path direction. Then find j dot dA, set up the integral, including the bounds of that integral. Calculate that integral for both inside and outside the wire. And then go ahead and put that all together with Ampere's law to find the magnetic field inside and outside the wire. Now remember, on number 3, you do not actually have to do the integral. You just need to do some multiplication. You just have to think about what that's going to be. And remember, your Amperian loop should have a radius that's, a variable, like s. Another reminder, we're using cylindrical coordinates. So that's going to affect how your dA comes out. If you need to remind yourself, we actually did this integral last week. The only difference is that now we're doing it with an inside and outside, so we have to do the funny business with the primes. Okay, so go ahead and work all this out and press play when you're ready to start checking your work. Alright, so what direction is that magnetic field? So our thumb is coming out of the screen, so our fingers curl around counterclockwise. So our magnetic field's going around counterclockwise in a circle. So I'm going to sketch that. I'm actually going to go ahead and write it down what direction that is. So that is the phi hat direction when it goes like this. If our current had been going into the page, our thumb would point into the page, and the current would, then the magnetic field would curl around in the clockwise direction. That would be minus phi hat. Okay. Now let's define our Amperian loop. Since magnetic field's going counterclockwise, I'm going to define this path to be counterclockwise as well. And I'm going to make the radius of this s, because that's the variable in cylindrical coordinates. Okay, so what's b dot dl? So we already did this just a few minutes ago, so we just need to multiply b times the length of the path, so it's b times 2 pi s. So the radius is, because that's our Amperian loop, it is not r because that's the thickness of the actual wire. And this is positive because we defined our path to be in the same direction as the magnetic field. Okay, what's dA? Well, remember in cylindrical coordinates we have ds, s d phi, and dz. This is varying. The area varies over s and phi, not in z. So you have ds, s d phi, and then we need to figure out our direction. So it's either going to be positive z hat or negative z hat. Because our fingers are curling around in the counterclockwise direction, our thumb is pointing out of the screen, so that's the positive z hat direction. I'm going to rearrange this just because I like to keep all my variables out front. Okay, now we need to find j dot dA. Okay, well j is ks times z hat. dA is s ds d phi z hat. Okay, z hat dot z hat is just 1, so we have ks squared ds d phi. Okay, so that I have plenty of room, I'm going to copy number 5 over onto the next page Keep going. Okay, for number 6, we have to set up this integral both inside and outside. So inside we have, it's a double integral. Inside, s goes from 0 to s, phi goes from 0 to 2 pi. That means we have to put our primes on our s's on the inside. And that's because the bigger the Amperian loop gets, the more current is going to be enclosed in our loop. Now outside, we're still going from 0 to 2 pi because we're still going around a complete circle, but now s goes from 0 to r, because once you get past r, you're not enclosing any more current because your loop's just including empty space. Alright, and you can put a prime on this s too if you want, but you don't have to. Alright, let's do our integrals. Now we actually did this integral last week, so I'm not going to write out all the details. The only thing that was different was that we didn't have to worry about primes, and I think we are using 0 to capital R instead. Oh, that superscript is too small. 3. Okay, then we're going to do outside. Again, we did this last week, so if you need the details of this integral, just check your notes from last time. Okay, now we just need to put this all together. So inside, what do we have? We have our path integral is b2 times s, so that's equal to mu naught times the total current enclosed. You can call that I enclosed or I total, whichever, it's fine. Sorry, my superscripts keep shrinking. I'm trying to remember. The 2 pi's cancel out. So we have an s cubed over here and an s over here, so that reduces down to an s squared. Now remember, we already decided that b's in the phi hat direction, so I'll go ahead and make that a vector. Okay, now we'll do outside. So our 2 pi's cancel. So now capital R cubed is a constant, so the power doesn't reduce. Again, this is in the phi hat direction. Okay, so let's make sure our result makes sense. So inside, we're finding that as S increases, the magnetic field increases. So the more current that's enclosed in our loop, the bigger the magnetic field gets. That makes sense. Now on the outside, what we see is that the magnetic field decreases 1 over S. So the bigger S gets, the smaller the magnetic field gets. So the magnetic field goes to 0 and infinity. Good. That makes a lot more sense than the infinite slab. So infinite wires aren't quite so confusing as infinite slabs of current. They're a little bit, I guess they're a little bit more realistic. And again, so if you have like a really long wire, but you're only concerned with a magnetic field in a very tiny portion, this will work for a real life situation just fine, even though we're doing calculations with infinities. This is a lot of time what you're doing as a physicist is you're saying, all right, what approximations can I get away with? You know how we like to make things as simple as we can, ignore friction if we can. But we just keep doing that. Okay. Now we're going to go through one last case. So we've done rectangular geometries with the infinite slab. We've done cylindrical geometries with thick wires. Now we're going to look at a solenoid. Okay, so we're looking at an infinitely long solenoid. Let me just review what a solenoid is if you don't talk about it much with your classes, or maybe you're just a little rusty. So a solenoid is basically just you have a long cylinder and there's wire wrapped around it. So you can kind of say that there's n loops per unit length. So say if this much was L tall and there were n loops here, I've drawn 4. So if there's n loops in L length, we'll get another number we'll call little n. That's loops per length. Okay, so basically it's stacked loops of wire. Alright, so some of you may already know what the magnetic field from a solenoid is supposed to look like, but let's think through it to make sure, even if you do know why it's that. So, if we think about how when we have a wire and we put our fingers in the direction of the loop, then our fingers have to curl around to tell us which way the magnetic field goes. So if we put our fingers through this loop, so in the front of the wire, our fingers are pointing to the right, so our thumb is pointing to the right, so our fingers are pointing up. So that's going to give us a magnetic field that goes up in the B direction. If you also think about it, it goes up in the Z direction. So if you also think about the back side of the loop and your thumb's pointing to the left, your fingers are still pointing up inside the loop. Outside the loop, if you put your thumb along the current, then your fingers start curling down. So you get a magnetic field that should point down outside the loop. That I'm drawing this might bother you if you already know the answer. But this is going to have to be what our first guess is, just based on the geometry of the situation. Because these loops are stacked infinitely, the magnetic field never really gets to finish curling around the top, and just stacking it creates the effect of a magnetic field that just points straight up inside and straight down outside. Now, something that makes you look a little bit less goofy with your fingers is if you just curl your fingers around the direction that the loops are going, your thumb will point the direction that the current's going. Your thumb will point the direction that the magnetic field is going inside the loops. And that's how my high school teacher taught me to figure out the direction of the magnetic field inside a solenoid. Okay, so what should we use for our Amperian loop in this situation? This is where things get tricky. When we have an infinite slab, it makes sense that we're using rectangles. When we have a thick cylindrical wire, it makes sense we're using cylinders. Now we have a cylinder, but the wire is wrapped around it. And our magnetic field definitely doesn't look cylindrical, it looks rectangular. So take your cues from the direction that the magnetic field is. Because our Amperian loop needs to be either parallel or perpendicular to the magnetic field at all points. So though a solenoid is a cylinder, we're really trying to line up with the magnetic field, so we want to use a rectangular loop. So let me just sketch that in there. Okay, I'm going to sketch my loop so that the path goes around up inside and down outside. So that's a clockwise loop. So this loop I want to sketch so that it encloses the current. So when we're doing a wire, we make it so that our loops are centered on our cylinder. Here, we're more centering on where the current is. So we're centering it on the surface of the solenoid where the current is passing through. Okay. Now, kind of a weird thing is you can draw this loop anywhere. So you could even draw it out here, totally outside of the solenoid, and say, oh, well, I have my loop. It's out here also. I'm going to call this loop where we're outside, number 1. I'm going to call this loop where we're actually enclosing current, number 2. This is tricky, and I remember when I first learned about solenoids and using Ampere's law on them, I thought, wow, this is a lot of cleverness. How would it ever occur to me to do this on my own if this was not shown to me? So if you feel that way too, I do not blame you. The key to remember is line up your Amperian loop with your magnetic field, not with a cylinder or solenoid. I'm saying this 5 times because this was what took me forever to understand on my own when I first learned this. Okay, so I'm just going to say that my loop is, I'm going to say it's L tall, and I don't really care how wide it is at the moment. Okay, so I'm going to say for my loop that's outside, I'm going to say it's the distance A from the center of the solenoid. And for the outside of my loop, I'm going to say that it's the distance B from the solenoid. So this distance here would be B minus A. Although that doesn't matter a whole lot. Okay, so far this seems like a weird thing to do. Okay, well let's just go ahead and use Ampere's law for outside loop. What's B dot dl? Alright, so we can start, say, on this side. If we look at the symmetry of the situation, there's no reason that B should be bigger at the top of this loop than at the bottom, so we can say it's constant with Z, but it would make sense. Just saying we don't know anything. It would make sense that the magnetic field would get smaller the further away from the solenoid we are. So I would say this is more like B as a function of S. So I would say, for this outside, I would say B at location where S equals B times L gives us the outside side of the path integral. Now this next side down here is perpendicular to the direction of the magnetic field, so that's 0. We come up this side. Well, now it's B at location A times the length. Now this one I'm making negative because here, remember, I said that the magnetic field should be pointing down, but our path is now going up. So that means that this line integral is negative. And then we come back around the top. It's perpendicular to the magnetic field, so we get 0. Okay, this is our path integral. L, okay, there's our path integral. What about the other side of Ampere's law? Well, we put this out here in the middle of nowhere, so there's no current enclosed. It's 0. So what's Ampere's law tell us? It tells us that L times this okay, so that tells us that the magnetic field at B equals the magnetic field at A. Well, that's kind of weird. We're getting the same weirdness with the infinite slab, and for the infinite slab we found that the magnetic field didn't vary with distance. That's what this is telling us. Okay, now here's another bit of trickiness that bothers me. But it makes sense. You would think that at infinity, yes, technically you're supposed to write B of S as S goes to infinity, take the limit. But I'm a physicist, so I'm kind of sloppy, so I just write B of infinity. You would think that infinitely far away from the solenoid that the magnetic field should be 0. But based on this, it can't vary. So what this tells us is that outside the solenoid, the magnetic field has to be 0 everywhere outside the solenoid. This is a lot of cleverness. Let me know if this bothers you as much as it bothered me the first time I learned it. And it's even more disconcerting when you do it after the infinite slab, because when we do the infinite slab, we say, well, I did all my work, that's what happened. But this is a little bit harder to follow. Okay. Well, there we go. So if you already knew what the magnetic field outside of a solenoid was supposed to be 0, there you go. It works out. Okay, now let's do inside. This one I think you can do on your own. I'll resketch it again on the next page for convenience. So now I want you to work this out for the inside loop, that loop I called number 2 before. So half of this loop is inside the solenoid, half of the loop is outside the solenoid. And remember, this loop has a height L. I want you to find the path integral around this loop, and it's going clockwise. And then I want you to find the total current enclosed by that loop. So here's your hints and extra information. So the current through one loop of that wire is I. There are n loops per unit length. So I haven't shown you how to find this total current enclosed, but see if you can figure it out. Okay, pause the video and try it out. Okay, so what we're doing is, well, for the side that's inside, we just have B times L, and the magnetic field and L are in the same direction, so that's just B times L. For this side that's on top, well, the path is perpendicular to the magnetic field, so that is 0. Outside, it would be B times L positive, except that the magnetic field is 0, so that's also 0. Then we come around the bottom, we're perpendicular again, so that's 0. So all we get is B times L. Okay, now to figure out the total current enclosed. Well, basically, the trick is to know that N equals N over L. So if you want to know the total number of loops of wire that are enclosed, that's just N times L. Then you multiply that times the current in each wire. So it's just the number of wires times the current in each wire. So this is the current enclosed. Okay, let me know if that makes sense. Alright, now I want you to put together this information to find the magnetic field inside the solenoid. Give it a go. Okay, so we have our path integral on the left side equals mu naught times the current that's enclosed, or I total, whatever you want to call it. So our L's cancel. That's good because we arbitrarily defined how tall our Amperian loop was. So the magnetic field is just mu naught Ni. And we already decided it's in the z-hat direction. So let's put that label on. Okay, so we have a magnetic field that's constant inside the solenoid. Alright, let me know what you think of that one. It requires a lot of cleverness. If you want to read more about some interesting geometries in your textbook, they talk about a toroid, which is a donut shape with wire wrapped around it. That one's an interesting one to try out too. Okay, so just like Gauss's law, Ampere's law is only useful in specific situations when the geometry works out. So for Ampere's law, that means when the magnetic field is either purely parallel or purely perpendicular to a path that we can define, and that the magnetic field can be constant along that path. In general, you have to use the Biot-Savart law, which is French, and I'm sure I'm mispronouncing it. I should look this up. And so that law, like Coulomb's law, will let you do more general calculations. However, that one has a cross product inside of an integral, and I really prefer not to get into that in this class because there's so many more interesting things we can do than dealing with cross products inside of integrals. And you can actually use that if you don't find this Ampere's law proof of the magnetic field from a solenoid convincing, you can use the Biot-Savart law to prove it, but we are not going to do that in this class. Okay, so that's all we're going to do with magnetostatics. So that, remember, is when we have steady currents and we want to find the magnetic field from it. Now, the funny thing about magnetism is, this does occur in our daily life. We have circuits everywhere, so we do have tiny magnetic fields arising all over the place. But normally when you think about magnets, you think of magnetic materials. You have a bar magnet. And so we're not really going to do the math associated with those. Actually, magnetic materials, so they are more common and more immediate to our everyday experiences, they're harder to do calculations for. I have included in one of your reading assignment options some more information about where magnetism in materials arises from. Basically, it comes from electron currents. And I'm going to say quote unquote currents because really it comes down to quantum mechanics. And we're just going to use a classical analogy. So magnetism in materials comes from the electrons orbiting the nucleus. So that is basically a current. So that can create magnetic fields. Electrons also have spin, and spin really is a quantum mechanical property, and that creates magnetic fields as well. And basically in some materials, all those little electron currents line up so that it adds up to a total magnetic field in the whole material. In some elements, it just all cancels out. And some of them you can get some magnetism if you apply a magnetic field to the material, that'll line everything up. And it's really interesting. But it's something I think we should only do conceptually and not try to do the math for in this class. But anyway, if you want to read more about that, the third pair of articles can tell you more about that. Anyway, so next week we're going to move on to electrodynamics because time is flying by and there's a lot of fun stuff to do in electrodynamics because we still haven't done everything with Maxwell's laws yet. Okay, well, let me know how you're doing. You'll have lots more practice with doing these in your homework. All right, see you. see you later.